Now that we've seen what a moment of inertia is, let's actually do an example. Let's see how to actually calculate this. So what we want to do is calculate the moment of inertia of a thin rod, such as this ruler, about 2 different points. So the first point is going to be about the center of mass. So what is the moment of inertia about this object here? And then also, what is the moment of inertia then about this end point? Now again, due to the structure of the moment of inertia, it depends on the distance, which again means that what? These masses out here, when it's at the center points, aren't as far away, which means the moment of inertia is going to be smaller, versus at this point down here, now these distances are much further, and since it goes as the distance squared, this is now going to have a much bigger moment of inertia. Now, what this also implies to us is since it depends on the distance, every different point that I want to take a rotation axis about has a different moment of inertia, which effectively means that any object such as this has an infinite number of different moments of inertia. Not exactly convenient, but it turns out these are all related to each other, and we'll talk about how they're related when we do the second portion of this. But let's see how we actually do the first person. So again, we want to take a thin rod. So this is my thin rod, and I want to find its moment of inertia about the center point here. So this is my center point, my center of mass. And let's say that this rod has a total length to it, so that total length is simply L. So now, since this is a continuous object, what this means then is for part A, the moment of inertia about the center of mass is simply going to be equal to then the integral of r squared then dm. Where again, dm is going to be equal to either lambda dl, a to dA, or rho dv, depending on the symmetry. Now, according to our picture here, and according to the fact that this thing is a thin rod, what this means then is that this thing only has a line symmetry to it since all of the mass is distributed across a line. Now, what I mean by thin rod is I basically mean that, even though I'm looking at a ruler here which has a thickness to it, imagine that this thing is 0 width in this direction, so only exists along the horizontal direction. So good. So how does this thing work? So let's put in a coordinate system. So let's say this is my y-axis. This is then my x-axis. What we're going to do is we're going to chop this thing up into a whole bunch of small differential masses. So let's pick this point randomly. So this is my small differential mass. So this thing has a mass of dm, and this occurs some distance x away from our origin. So according to this then, since this is our position vector according to that origin, r is simply the same thing as x. These two are the same. Now, since this thing also has line symmetry, what this means then is that dm, we're going to rewrite as lambda dl, where dl then is the width of this differential section that we're cutting off. So this width across here is simply our dl. Now, since this is along the x-axis, what this means then is that dl is the same thing as simply dx. So this is going to be rewritten as dx. So this means this is going to be equal to lambda times dx. So if I plug that in, this is now going to become equal to the integral of that x squared times lambda times dx. But I want to integrate over all the places at which the mass actually exists, where the mass only exists from this end of the rod to this end of the rod. Now, according to our picture, this end of the rod then is going to be at minus the length of the rod divided by 2, where this length here is going to be at the end of the rod, which is also going to be L over 2, just without that negative sign. So this thing now is going to become lambda, where I'm assuming this thing has uniform mass density, so I'm going to pull that out, is integrated from the end of the rod to the other end of the rod, so minus L over 2 to L over 2, of then x squared dx. Good. So do that integral. This is now x squared dx. Integral of that is x cubed divided by 3. So this thing is going to become, so let's write it over here. So the moment of inertia then, about the center of mass, is going to be lambda times then x cubed divided by 3, evaluated from minus L over 2 to then L over 2. Now here, this minus is important because remember when I evaluated the bottom bound, I get an extra negative sign. But when I have a negative cube, that's the same thing as a negative. So this is going to be the same thing then as lambda divided by 3 times L over 2 cubed minus minus L over 2 cubed. But again, this negative cubed is the same thing as a negative, so this negative is going to cancel this one, which is going to make that a positive. So I actually get 2 factors of that guy. So it's going to become L cubed over 8 times 2 of those, which is the same thing as L cubed over 4. So this becomes then lambda L cubed divided by 12. Now again, lambda, remember, is the total mass divided by the total length. So lambda is the total mass divided by the total length. So if I substitute that in, all it's going to do is kill off one of these. So then the moment of inertia about the endpoint is then simply equal to the total mass of the object, where if this thing has a mass of m, times the length of it squared divided by 12. So it's 1/12 the mass times the length squared. So this is the moment of inertia about the center of mass, about this point. Now for part B, again, what we want to do is we want to find the moment of inertia then about this point down here. Now, what we would have to do then is if this was all we knew, we would have to redo this integral defining a new particular coordinate system. So in this case, we'd have to put our coordinate system at the end of the rod. Everything would stay the same except for the bounds of the integration. So in this case, instead of integrating from 0 or from minus L over 2 to L over 2, we would now integrate from 0 to L. Now, all that's going to do is it's going to make this L cubed. This is now going to become 0, so this is now just going to become lambda L cubed over 3. And again, using this substitution for him, this is now going to become mL cubed over 3. Now, we don't want to do this integral every time, so let's talk about something else which is going to make our life more useful, or at least more helpful, and this is what's known as the parallel axis theorem. So what is the parallel axis theorem? So the parallel axis theorem says if I have an object, here's my object, and I want to rotate it about this point here, let's call this point P. This says that I can determine the moment of inertia about point P by simply knowing, first of all, the moment of inertia about the center of mass, and the distance point P is away from that center of mass. So what this says then is that the moment of inertia about point P is then equal to the moment of inertia about the center of mass, plus then the mass of the object, we're going to call it little m in this case, times that distance d squared. So this is what we call the parallel axis theorem. So again, all this means is if I have parallel axes, which means in this case I'm rotating this way about the center of mass, in this case I'm rotating this way about this point, all of these moments of inertia at any point parallel to the center of mass are all related in this way. But if I have a rotation axis which is perpendicular to that, for example, instead of rotating this way, I want to rotate this way, that's something more complicated that we're not actually going to talk about, but that's what's known as the perpendicular axis theorem. So we're not going to talk about that here. All we care about then is this parallel axis theorem. So what this means then is that, if we go back to our thin rod, so here's my thin rod. Again, this is my center of mass location. This is the point P. Now we want to find our parallel axis theorem about, or moment of inertia about. And again, this thing has a length of L. So in our case then, we know that the moment of inertia about the center of mass is equal to 1/12 the mass times the length squared. The distance then from here to here is simply half the length of the rod, so this is going to be L over 2. So according to parallel axis theorems then, the moment of inertia about the endpoint is then going to be simply equal to the moment of inertia about the center of mass, plus then the mass of the object times the distance at which I am away from that center squared. So this is the same thing then as what? 1/12 plus 1/4, all then times the mass of the object times the length of it squared. So common denominator is a 12, so this is the same thing then as 1/12 plus 3/12 times the mass times the length squared. That's the same thing as 4/12, which is simply 1/3, which is then 1/3 the mass times the length squared, which is exactly what we said it should be verbally. So what the parallel axis theorem is going to allow us to do is to simply find the moment of inertia about any axis that's parallel to that center of mass. Now, why this is useful is your book has already calculated a whole bunch of moments of inertia about a whole bunch of different sets of masses for different objects. So when you want to then find the moment of inertia for a particular object, you would just simply look in your book and then find that moment of inertia typically about the center of mass. And then, if that moment of inertia is not about the center of mass, all you then have to do is apply the parallel axis theorem to then rotate that moment of inertia point to any particular point at which it is that you want. It's going to save a whole bunch of time, and that means you don't ever have to do that integral again, unless it's some sort of irregular shaped object, which we just have to do the integral for. But again, in most cases, your book has already calculated a bunch of them. All you have to do is look up what it is in the book, apply the parallel axis theorem if needed, to then move it to whatever axis that you want.